for a vector going this way, another vector going that way, two different vectors. So if you do an experiment, like tossing a coin, when it lands on the table of this quantum coin, it's going to be this vector or that vector that corresponds to it with some probability. Now, what does the probability mean? We have to go back to the classical definition of probability. That is, if I keep repeating this thing, you know, if you and I have a little gambling going on here, all right? So if it's head, I get $1. You give me $1 if it's tail. So if we keep doing that, we basically would even out. If we do it 1,000,000 times, looks like there's $1 million changing hands, but it will be a very friendly game. At the end of the day, neither of us would go broke. Well, that, of course, it's not completely true, but it's close enough. So the probability just tells you if I do lots of experiments, but if I do one experiment, of course, you know, I only get one result. So that is the state of the theory. So you say, what is the use of that? Why is that useful for making technology? Here's the point. You can use it for quantum information processing. Well, what is information? Oh, 0 and 1 is a bit of information. That you know from just the fact that we have computers, right? 0 and 1 is we call a classical bit of information. The computer scientists call it, and you all heard about 0 and 1. Now, so the 0 and 1 can be a physical state. So I could use coins, but I could use other things that has the properties of high and low and stuff that to represent and to actually make a machine, make a computer. And for off, that's the information. I can code everything in 0 and 1, send it off. I could code a picture of us here and send it off over the broadband, and then they will receive it and reproduce this picture, right? We're so used to it that we don't actually think about how it happens. That's information processing. That happens to us now, all the time. Now, the quantum one is that I don't have to send, if it's 0, I would send one picture, and 1, I would send a different picture. I can send the same vector, which is a linear combination of the amount of 0 and 1. So if I want a dark spot, let's say I would send H. If I want a light spot, I would send a P. There's no halfway in between, but it doesn't matter because I digitized the information. Okay? But here, when I send a quantum mechanical state, it's actually, I have a possibility of both. And later on, I'll sort it out. But what later on I do is that I'm going to sort them all out. I'm going to actually do things, both possibility at once. So therefore, instead of having to send 1,000,000 different pictures, I'm sending about, let's see, about 12 little vectors. In other words, in the computer language, I'm parallel processing the two possibilities. If I were doing calculations, I don't have to do a formula, use a formula and do this once with this one is 0 and 1, this one is 1 and 0, and so on. I can do it, all of them at once. So what that means is that mathematically, I can also, if I have a number that's 2 powers to the n, I just have to do it to the power. So you see that is much more economical. Not only for information processing, it's fast, and for quantum computer, it means that it's exponentially fast because you're using the exponent. If you think that the modern computer is fast. When you change the principle of this into a quantum computer, in principle, you should get it really, really fast. You say, well, why do I need it that fast? I can't comprehend it. Well, there's certain things we cannot do now. One of the things is if you have a very big string of digits for integer, you can't factorize it. You don't know what two factors. I can tell you they're given by two prime factors, and you wouldn't be able to find it, at least not in any useful amount of time that you have. So the banks use it for coding, for cryptography, so that you can go online and nobody can steal your money. That's a very useful thing. So you are saying, if I can have a computer, I can promise you that we can go and steal the money by breaking the code. How's that? But for everything, there's always something else that could counter it. There's a quantum cryptography, on the other hand. You can send in an object that has both properties of 0 and 1. So then you can make a code. It's not that it cannot be broken, but if somebody actually breaks the code, the receiver of your message immediately finds out. Right away, he can call you on the phone and say, somebody has been stealing our information. Stop or change the thing. So, it's like science fiction. So that actually is interesting. So it's like the ancient Chinese fable, right? So here I promise you a spear that can penetrate the shield of the code. But then I promise you a shield that no spear can break. So that's the Chinese name for paradox. So, but that's fine. Then it all, as a gambler would know, everything is on the margin. Then you have to talk about little details of who is going to do what that can be on top of the situation. So there are these possibilities. The other thing is that simulation. One of the things we would like to do is that it's great to be able to do experiments. So everything I talk here is based on experiment. But with more and more computer power, we can simulate. Now, the advantage of simulation is not just to reproduce nature, but you can then, you can then change. It's much easier to change your computation, as you know, right? For those of you that do computation and get a different result. Then you can go into the lab and try to change things and get different things. For example, I was told by the biologist, and they were very interested in what Walter Kohn and I were doing. I say, why? They say, oh, did you know that in these biomolecules, if it's right-handed, like the helix, if it's right-handed, this thing is a poison. But if you can make that left-handed, it's actually a very effective medicine for something. Their cohesive energies are not very different. I don't want to know the energy because they're about the same, but I want you to calculate the structure.